Hello everyone. In this lecture we're going to see the first law called Kirchhoff's current law. It's really the first of the two Kirchhoff's laws that exist. We're going to call it KCL for short, and it's essentially one of the two main laws that we're going to use to analyze circuits. Before we go to the details of Kirchhoff's current law, I want to make one specific comment. So Kirchhoff's laws are essentially derived from more general physical laws that exist. Specifically, they are derived from Maxwell's equations, and Maxwell's equations are not derived by anything. They are simple physical laws that we know they're true because of our experience. So when you hear the name law, I do want you to keep in mind that those are derived from other more generic equations. Why is that important? It's important because essentially those laws, strictly speaking, apply only for DC circuits, apply only when we have a constant voltage and a constant current. When the current starts becoming AC, starts alternating, those laws, strictly speaking, are not correct. However, in most practical situations, they are extremely good approximations, and we will still keep using them until the frequency of the alternating current is so high that those approximations truly break down and we can't use them. So keep those disclaimers in mind, and let's go ahead and study Kirchhoff's current law. So the Kirchhoff's current law becomes very useful to us when we have to understand how currents split in junctions. Let's look at, for example, the circuit that you see right here. This is a circuit that includes multiple devices, and when we have multiple devices, we somehow need to connect them, and we connect them through nodes. So every circuit will have different nodes. Some nodes will connect just two devices. So this node right here, for example, is connecting simply two devices back to back, while other nodes will connect more than two devices. They will connect, for example, three devices. So here is a node that connects those three devices. This blue node that you see here is essentially connecting three devices. So Kirchhoff's current law applies to all nodes in a circuit, whether they connect two or more devices. However, it's far more useful when we are talking about nodes that connect three devices or more. So to make that distinction easier to communicate, I will go ahead and more precisely define the concept of a node. So a node is essentially a connection point in a circuit, and I will say a node is a connection point with two or more devices. So this green node that I showed you in the very beginning is essentially a node that connects two devices. On the other hand, an essential node is going to be, again, a connection point, but now with three or more devices. And the reason we make this distinction is that when you have three or more devices, the flowing current will actually split. So, for example, when we had a node, this current I1 will go through this device and will necessarily continue through the second device. It really has nowhere else to go. On the other hand, when we're talking about essential nodes, the incoming current does have a second path that it may follow. So it could actually go up and become I2, or it could continue straight and become I3. That current will basically split, and we have to find a way to calculate how this split will happen. Now, from the terminology I have used so far, you may actually be wondering whether I'm talking about electrical current flow or whether really I'm talking about water flowing in pipes. Well, for DC currents, they're essentially indistinguishable. Or as many people will say, DC current flow is nothing else but water flow in pipes. And exactly the same way as you were thinking about water flowing in pipes, if you have water flowing here, and this water essentially faces a junction, that water flow will split. And the way you're thinking about splitting is that a wider pipe will carry more water than a narrower pipe. In a very similar way, when we talk about DC current flow, and I have this I here, when that I comes to node A, it will have to make a decision. And that decision will depend on how big of a resistance each of the resulting branches will present to this current. if I make the assumption that this resistance is identical for all three branches, then really the current will split into three equal parts, which will continue flowing through those branches, and eventually they will come to node B, and they will essentially be recombined together. You might say, well, what's the big deal out of all of this? It seems obvious. It seems that that's exactly the way it should be. Well, the big deal of that is that there is no way for you to destroy or generate new current at a node. So let me say this again slightly differently. There is no way for you to generate or destroy charge flow at each current node. There is a very basic physical principle that actually guarantees this for us. And the basic physical principle is that you can't generate or destroy charges. There is no way, in other words, to take an electron and just destroy it. And there is no way to generate an electron out of thin air. And because precisely of that, if I'm thinking about this node B here, and I know that I'm having three currents flowing from the left to the right, then those currents must sum up to get me this current I here, because if they were not, and let's say this current I was twice as high as adding those three currents, it means that somehow I generated electrons out of nothing. So this basic physics principle that I just mentioned is called conservation of charge. And it is exactly the law that Kirchhoff's current law is based on. So this conservation of charge, once again, guarantees for us that we cannot generate or destroy any charge in the universe. When the universe was created, the amount of charges was set, and we can't do anything other than that. Now, in order to become easier for us to express the conservation of charge, we have come up with some mathematical expressions which I would like to present right now. So if I consider a node in a circuit, and I have now zoomed into a particular node in a circuit, in general there will be a bunch of currents that will flow into the node or a bunch of currents that will flow out of the node. And so I could say, in order to apply the conservation of charge, that the total amount of current that actually flows into the node, I will represent this as sigma I in, must be equal to the total amount of current that will flow out of this node. That seems perhaps the most obvious to you. Maybe that's the way we should basically expressing the conservation of charge, or KCL. However, there is an easier way to do that, and by easier I mean it's easier to avoid making mistakes because you're consistently applying KCL. And that consistent way of applying KCL is to simply say that the amount of current that flows outside of this node must be equal to 0. So let me put the words in the blue box in the slides, and I'll say this again. Essentially, it says that the sum of all currents leaving a node in a circuit must sum up to 0. In this case, in this example I'm showing you here, every single node, every single current is actually flowing out of this node. From I1 to I8, the arrows point outside of this node. So if I wanted to write the equation I wrote here in words, but I want to write them in a math form, I would write that I1 plus I2 plus I3 plus all the way to I8 must be equal to 0. Now you might say, but why do you write it this way? It's really impossible for all the currents to be flowing out. Indeed, that's true. Some of these currents, in fact, will end up flowing in, which means that some of these currents will have a direction that is different than the one that is assumed by this figure. For example, the true amount of current of I2 may actually be flowing into the node, but I have assumed direction of I2 to be out of the node. It's okay. It's perfectly fine to assume a direction, solve the problem, and if the result is actually negative of what you found, it simply means that the true direction is different. The benefit of applying KCL, as I'm showing you here, meaning by saying that the sum of all currents leaving a node must be equal to 0, is that if you apply this every single time consistently, you will dramatically reduce the number of mistakes you will make. versus always trying to think, oh, do I take this current as inward or outward? Do I write sigma in is equal to sigma I out? Don't fall into this trap. Always apply the conservation of charge, always apply KCL in the same consistent way, no matter what the situation is. Trust me, if you do it that way, you will make far fewer errors than if you have to spend every single time enough time to think about what's the right way to apply KCL. So, thank you for watching this video. Here you actually learned of what KCL says, what's the basic physics principle behind it, and how to apply it every single time. Thank you very much. See you next time.